Hi, welcome you all to our course Introduction to Biostatistics. So, this is our first lecture. I just wanted to cover one lecture on what statistics is, what biostatistics is, and then talk about few things which are of important and which will serve as landmarks as we go ahead in this course. So, I will begin with the course material, what is the courses that we are, the two main reference books that will serve for you in this course. So, there is the first book, Introduction to Probability and Statistics by Mendenhall, Beaver and Beaver, and the second one, Introduction to Probability and Statistics for Engineers and Scientists. So, both these books are available on Flipkart or Amazon and on regular websites. So, I come to the first question, what is statistics? So, statistics is the science that deals with the collection, classification, analysis and interpretation of numerical facts or data. For example, we continuously hear about the US elections right now, and every now and then you see an opinion poll. What is the statistics by which Hillary Clinton will beat Donald Trump in the polls? You have the statistics which is repeatedly taken, and you still come up with different companies which hold this polls which come up with different numbers. So, one person might predict that Hillary Clinton will win by 30% votes, another predicts by 20% votes. So, this gives you an idea that this process is extremely complicated. It is very easy to come up with a number saying this is the difference or that is the difference, but there is a very active science behind this process in order to make sure that the numbers you pop out of the process are accurate. Another example I want to talk about is the weather patterns, right. Every year in our country we have the meteorological, the weather department which predicts whether the annual rainfall in our country will be as is it good enough for this year, will it beat expectations. For the past 1 year we have all known that India has faced a severe drought for the last maybe 2 consecutive years. This has been particularly extreme in parts of Maharashtra where I stay. Okay. So, in all these cases the prediction which these agencies give are really taken very seriously, even for the government to make a informed decision as to what should be the steps if the rainfall is adequate. What are the steps to make sure that the water is uniformly distributed? Should there be a water cut in the case that rain is not up to expectations, or if there is excessive rain, should the dams release the water? As a consequence of that, there might be some flood like situation created in some other place, as has been recently observed in Bihar. The last case is, for example, income as per professions. We continuously decide, particularly when we are finish our education in class 12, we ponder as to which trajectory we want to choose. Of course, everyone wants to be an engineer, but the simple reason is we have enough industry positions open, which after our bachelor's we can get access to a job which will secure your future. So, that is of course not true from every profession, but every profession has its challenges. So, for example, if you want to be a singer, then the trajectory you will go ahead in terms of income, initially you will have very minuscule amount of income, but as you become established in your field you will have more and more income. So, what is biostatistics, right? So, biostatistics is nothing but application of statistics for the study of living organisms, for human beings, for animals, or for any biological process for that matter. So, we can take examples from any field which concerns biology or medicine or bioengineering. Biology, for example, we want to talk about evolution, for example, right. In evolution, we want to see by, let us say, comparing the structure of the bone, how a dinosaur eventually became a bird, so on and so forth, and these kind of things you want to make exact analysis of specific structural components of a particular component of the body, let us say, and see its evolution as a function of time. In medicine, right, you want to predict the ability of drug resistance to arise in a given population. Given that in the past it has become resistant to this particular drugs, what is the chance that they will become resistant to this new drug which is probably the company is thinking of bringing to the market. Last case, for example, is in public health. You have all been aware of the damage that Zika virus is currently producing, right. So, in this case, in the case of Zika virus, whenever you go to the airport and you will see that people coming from these places must have a mandatory health checkup to eliminate the possibility that that person is a carrier of Zika virus. So, these are examples where statistics has been used to make some informed decisions, first to measure, and based on that measure to come up with some analysis, and then based on analysis to make some predictions as to what should be the corrective step. Okay. So, if I look at the history of statistics, it actually started with trying to understand the process of gambling, which is one of the oldest professions people have participated in, and this has roots in development of probability distributions which have been developed by De Moivre and Laplace. In the 19th century, for example, you have Galton's discovery of regression, Carl Pearson's work on parametric fitting of probability distributions, and that has, and of late statistics is particularly of particular relevance to the field of biology, biomedicine, and its applications in clinical science. So, why study statistics? Let us take a sample case. Let us say you are clinical coordinator for a clinical trial. You are enrolling patients at X locations, let us say X is 5 or 6 as the case may be, and you are pondering whether you want to add a new site for that clinical trial, right. So, for this, for getting approvals for doing these clinical trials, you need to get approval from the institutional review board, and one of the members of the IRB asks, okay, you want to add one more location, but what is your stopping protocol? You have no idea, right? What is the stopping protocol? Well, stopping protocol is those set of rules which enable you to either declare your clinical trial a success at an earlier time, or to preempt the clinical trial if you already have some negative data coming, because you collect data in a continuous manner. So, you have thresholds at various stages of data collection which enables you to label the clinical trial a success at an earlier time point, or to label it a failure. So, you want to minimize your losses, and so on and so forth. Another example, let us say, of biostatistics is measuring cell motility, right. So, inside our body, cells are not sitting steady in our position, right. There, many of the cells are continuously moving. Take the case of immune cells. They are continuously moving and scavenging for foreign particles which have come inside our body. We want the immune cells want to preempt it. So, the cells want to be able to move all over the place. Now, let us say in the case of cancer, or as the disease may be, you want to come up with a drug which inhibits this motion, right. Cancer is a disease in which certain cells which are supposed to be in a certain organ, they start migrating, they start proliferating, that means they start dividing, and then at some point of time they actually start invading the entire body. They eventually reach secondary tissues and stop their function, leading to death, right. So, a significant amount of effort by scientists is in trying to find out drugs which target cell motility, or the ability of the cell to move. So, you want to quantitatively assess whether this drug or drugs that you have currently developed in your lab, whether they work, whether they inhibit cell motility, right. So, and in your lab you have this experimental assay in which you can have single cells which move, right, which move randomly in your under the microscope. You are acquiring these movies, and the question here is, right. So, you want to understand the role of a specific protein or the effect of the drug, as the case may be, and so as a process you want to measure the cell motility and see whether it has an effect or not an effect, right. So, you want to essentially measure the cell movement. So, the question is, how should we acquire the movie when the cells are moving? Let us say a cell is jiggling in one place, right, it is not moving. So, over the let us say within 5 seconds the cell is pretty much static in one position, but over 5 minutes it is actually moving by a distance equivalent to its own length. So, if you acquire every 5 seconds, then essentially the information you are gathering is noise, but the information that you can gather is, if you acquire after 5 minutes, maybe that is an optimal time scale. If you measure after 10 minutes, that may not be good enough, because the cell might have come back to its original position, and to you it seems that the cell is static. Okay, so, how fast you acquire these images is an example of how you can statistics can help you in understanding what should be your acquisition speed, right. Let us take another example of a protein, right. Proteins participate in various functions in our body. When protein function is perturbed, then they stop working and then they lead to disease processes. Now a protein, you can imagine a protein like a long string which has loops in it. So you have these loops, right. These loops are actually, they hide some sites on them which other proteins ideally can recognize, but because these are in looped configuration, these sites are hidden and the cell cannot, and other proteins cannot see, which means they cannot bind, and then the downstream signaling cascades are absent. Under the conditions, you want to understand what is the statistics of protein folding, how much force do I need to exert for a particular domain of a protein to unfold. For that, what you can do is you can use techniques like atomic force microscopy to pull on the protein, and what you will measure essentially is the force which is required to open up a given domain. Now the question here is, so this force is not going to be a constant, it will give you a distribution, which means, let us say for one particular experiment for a given domain of a protein you get a value of 10 piconewtons, in the next realization of the experiment you get a value of 12 piconewtons, the next one you might have a value of 8 piconewtons. So it is, so there are small differences in this, but if you take it enough number of times, if you acquire enough number of data, then what you probably will get is something called a Gaussian distribution or a normal distribution, and the peak of that Gaussian distribution you can say is the force required to unfold that particular domain. One last example, okay, of an example of how biostatistics can be relevant. So cancer, again taking the case of cancer, cancer is consists of cells which are heterogeneous, right. So as these different colors are used as to make out that you have cells of different types. By different types, it might be the cells are of different sizes, the cells are of they are different extents of deformability, one cell is stiff, one cell is soft, so on and so forth, right. So you want to find out a process whereby you can understand and differentiate these phenotypic differences, and then so statistics, so you measure all these quantities for, so you have multiple parameters, size, stiffness, expression of some surface protein of interest, so on and so forth, and then given for each cell type within the subpopulation you get its phenotypic characterization. You want to understand what should be the combination of these metrics that would enable you to separate them into different lots. So again here the role of statistics will help you in identifying the number of subpopulations and their properties. Okay. So what are the types of studies which fall under statistics? What kind of, how do statisticians acquire data? For example, one of the most common is surveys or cross-sectional studies. So the important point about surveys is they want to collect information pertaining to the population which is right now, right here, right now. So for example, a particular company, let us say Airtel, might want to know what is the patterns of texting in college campuses by students, right. How many number of text messages do students on an average send, so that they can accordingly decide how many free SMSs can Airtel offer versus after how many times do they charge. So if they overcharge, then essentially eventually the student population will go ahead and sign up for some other company. So you want to retain your consumer base yet maximize your profits. So survey is a critical example of how this might help. Another case is a retrospective study. So retrospective study means you have a population of people who might have been exposed to something. Let us say yesterday I went to a restaurant, particular restaurant, I had my food, and today there is a food allergy or outbreak of food poisoning. So there is this investigative agency, they want to know whether is it because of one particular food that we have consumed because of which this food poisoning is occurring, or is it a random event. In that case they would want to you want to sample people who have visited that particular restaurant on that given day and compare with other people of similar demographic background but who have not gone to that restaurant. So, this is an example of a retrospective study. Another thing can be a prospective study. So, in prospective studies, these are studies associated to see, for example, in college campuses, as when the student population starts smoking, and you want to at what point of or how long of smokers will eventually lead to a chronic disease like a lung cancer or anything, but which have long latency period. So, the disease does not manifest itself in 10 days or 20 days, but we are talking about years, maybe 10 years or 15 years. So, statisticians would preferably like to track certain people over time to see how they have, what is their incidence of lung cancer, or what is their current state as when they started smoking to that current state. And of course, the final sample very often used, particularly for biostatisticians, is clinical trials, right. So, clinical trials are performed. So, after you have proved that a drug works in the lab, before we humans start taking that medicine, it has to be proven two things. One, that if I consume that particular medicine, I am not going to die. So, I do not suffer any extreme diseases or side effects, and two, that the medicine actually works, so that it can be put to the market. So, there are lots of studies, how what should be my study size in order to test whether a particular sample drug is working or not working, so on and so forth. Okay. So, in all these processes, there is a critical component of sampling. In essential, you have a population which is this big. So, in India, for example, we have huge population, and let us say I want to make a soap, or Patanjali wants to come up with its new toothpaste or some other product. It wants to test on a sample, right. It wants to do that measurement on that sample and ask, okay, to test whether my product is good or bad, what should be the price of the product, so on and so forth. I have to have that questionnaire in terms of a survey, but I want to ask some people. Now, how many people should I ask? Is it 10, 20, 200, 2000? So, of course, you cannot ask every goddamn person on this earth, okay, or every person in a city. You are still going to sample. Again, what is your sample? The kind of population, from the population you might draw multiple samples, right. For cities like Mumbai, Delhi, Madras, you might draw a certain kind of people to get feedback on how that product might do. In a more town-like area, you might go to much smaller towns, and the statistics, the information you will get might be completely different. Okay, but say as an exception, let us say if you are just doing it on college campuses, maybe it may not be that different between a city or a town. So, choosing your sample and the type of sample and the sample size represent two of the most important choices that we must take. Okay. So, and as an example of how wrong choices can lead to complete mess. So, there's a magazine in the US called a Literary Digest. So, it conducted a poll in 1936 and about the presidential poll, and wanted to ask who would win, Landon or Roosevelt. So, the particular magazine came up with a prediction that Landon will be victorious, but which did not happen. Not only was it a borderline case, but it was a significant victory for Roosevelt. So, this was a clear failure for that particular poll, and no wonder the publication actually stopped shortly. So, it is very important to make predictions which are reasonably accurate, and we will see repeatedly in India in election cycles, you have every TV, every major channel has its own prediction as to what it happened, and still in spite of all the checks and balances, still there is reasonable amount of heterogeneity in the prediction as to who will win and by what margin they will win. So, that brings us to sampling, okay, and what is the type of sampling? Okay. So, in terms of type of sampling, the most simple thing is simple random sampling, which means that I want an unbiased view of the population, okay, which is, so let us say in classes I want to measure the average height, average height of the class. I just ask 5 random students, I even blindfold myself, I randomly walk around, pick a student and measure her height, and that will give me an average height. Now, imagine I am doing the exact same thing, but I only choose only girls or only boys. So, of course, my measurement is going to be skewed, right, because on an average boys are slightly taller than girls. So, my average height number that I come up with is going to be erroneous. Okay. The other sample is systemic sampling. So, let us say you already know the population, okay, or the sample list. Okay. For example, let us say the class is the population, and I want to measure 10 out of 10 measurements, whatever be it, height, weight, or some other age from the population, and I know population size is 50. So, what I do, I arrange the entire population by name, by let us say by ascending or descending order of surname, and out of the 50 I choose number 1, then I want 10, so roughly your spacing is 5, I choose number 6, so on and so forth. Okay. So, there is randomness, and still I am not biasing myself, but I have kind of made it in a much more systematic manner. So, if your population size is reasonably known, then this systemic sampling is very commonly used. The last one is stratified random sampling. Let us say, for example, you have a basket of balls which are of 3 types, of 3 different sizes, right, and on an average you know what is the ratio of the total number of red balls to blue balls to yellow balls, right, 3 colors, let us say balls of 3 colors, and you know the size, the stoichiometry of red to blue to yellow, right. Then logic would dictate, if you are doing a random sampling, then the number of balls you would draw would be in proportion to them, okay, proportion to the colors. So, this is this is called stratified sampling. Okay. Let us get over a very simple, do a very simple case of simple random sampling. Okay. So, let us say you have 6 patients, right, and I want, and let us say we name the patients A, B, C, D, E, F, and we want to pick 4 of the 6 patients. Okay. I want to pick 4 of 6 patients. So, what do I do? What I can do is I want this process to be completely random. Okay. So, what I do is I choose. Okay. So, if you have A, B, C, D, E, F, there can be total of 6 C4 or 15 combinations possible, in which you have 4 different patients being selected. So, let us say ABCD is one example, ABCE is one example, ABCF is one example. So, if you write down the details, you will see that there are roughly 15 combinations possible, right. So, I want to draw 4 patients from 15 samples, and I want to ensure that it is completely random. What I do, I assign A, B, C, D, so there are 15 of these combinations possible. To each combination, I assign a unique identifier. Let's say, so A, B, C, D is identifier number 1, A, B, C, E is identifier number 2, so on and so forth. Okay. Now, from these, so what I do, so I have a total of 15 numbers. Now, imagine I break down the number 1, 0 to 1, that range, into 15 equal intervals, right. So, your interval, the size of each interval is going to be 0.067. Okay. So, the size of each interval is going to be 0.067. Okay. So, what you do, so you take up a uniform random number table, right. You choose any particular number and convert it into decimal. Let us say we chose a particular number, it is 25697, right. So, I can just put a decimal at the front, that is 0.25697, right. Now, given that I have broken the entire range, so if I have broken the entire range 0 to 1, so I have broken the entire range 0 to 1, 0 to 1, I have broken down into delta. Okay. So, this delta is equal to 1 by 15 equal to 0.0667. Okay. So, whenever I choose, when I am in this, I choose my identifier 1, which is the number, which is the combination A, B, C, D, right. When I choose 2, my 2 is my combination A, B, C, E. Okay. So on and so forth. So, from the table I had chosen a number, let us say 26897, right. I convert it into decimal place. So, I know this, so decimal place means, so my delta is 0.0667. So, 0 to 0.0667 I choose identifier 1, 0.0667 to twice of 0.0667, I choose identifier 2. So, like this, I think this 0.26897 should be identifier 5. So, accordingly, I can choose one particular combination of the patient. Okay. So, this is a way of doing simple random sampling. Okay. So, that is pretty much what would give you an idea. This is just the background idea of what means statistics. And so, to summarize, so we started off the definition of statistics, which is essentially science. Statistics is nothing but the science of numbers, okay, and biostatistics is application of statistics to the field of biology or biological processes or biological systems, and it has applications in basic biology, in medicine, in healthcare, in public health, so on and so forth. Okay. So, after that we discussed about the some examples of how statistics might be beneficial in our understanding of biological systems. Okay. So, I gave you an example of clinical trial, how to design a clinical trial and what to understand from that. I gave you an example. So, you need to understand how clinical trials are designed, right? What is the sample size of a clinical trial, so on, and also be acquainted with the jargon of a clinical trial. I gave you the example of cell motility. This is an example where statistics help you to understand that at what rate should you acquire movies, so that your movies are exactly so that movies are not artifact or not noise, don't give you noise when something is just jiggling in place versus something is data, that means cell is actually moving from one place to another. But you also don't want to miss too much of the information. So, if you sample too infrequently, then you are losing information as well. So, statistics will help you to get that information. We discussed the case of protein folding, protein unfolding, and how force can be used to open it, and you can measure what is the average stability of a domain by doing experiments, pooling the data, generating a distribution, okay, and getting to understand what this means. Okay. And last, talked about how you collect these samples. So, in terms of sampling techniques, random sampling or bias sampling, and you want to do it retrospectively as a survey, so on and so forth. So, this is just our first lecture. So, from our next lecture we will start talking about how to measure numbers from an experiment, from the raw data. How do you go about generating a plot? That is very important, and how to represent that plot, so that the common man or someone in the audience, be it scientific, non-scientific, they can understand how to what is the gist of the data. You cannot just show the entire raw data, but the useful metrics from that raw data. So, first step of that is actually to plot and convey what it is. Okay. With that, I thank you for the first lecture. I will also upload a few MCQs, so you can get an idea of what we discussed and get to refreshen your memories of this class. Thank you.